Hi, I'm deGrasse, and today I'm going to tell you 100 amazing facts about the Big Bang that you don't know. Subscribe, and let's get started. Number one, what is the Big Bang? The Big Bang is the main scientific idea about how the universe began. About 13.8 billion years ago, all space, time, matter, and energy were in an unimaginably small, super hot, super dense state. Then everything began expanding and cooling. As it cooled, bits of energy became particles, then atoms, then stars, galaxies, and eventually planets and life. Number two, was the Big Bang an explosion in space or the expansion of space itself? The Big Bang wasn't like a bomb exploding into empty space. Instead, it was space itself stretching and growing from an incredibly hot and dense state about 13.8 billion years ago. Imagine dots on a balloon. As the balloon inflates, every dot moves away from every other dot. That's what happened with galaxies. Space expanded, carrying everything apart. When did this happen? Again, 13.8 billion years ago. Number three, Big Bang is a moment, not a place. Many people imagine a big explosion happening somewhere. But the Big Bang wasn't a blast in space. It was a moment in time when all of space started stretching. This means there is no center of the universe. Everywhere you look, space is expanding from everywhere else. It's like if the universe is a balloon and the surface is every point in space, as the balloon inflates, every point gets farther from every other, but there's no one place where the inflation began. Number four, did time exist before the Big Bang? Scientists say that time, as we understand it, began with the Big Bang itself. Before that moment, there was no before, because both time and space are tied to the universe. And the universe started then. So in physics, asking what happened before the Big Bang is like asking what's north of the North Pole. It simply doesn't apply. Number five, who originally proposed the Big Bang theory? The Big Bang idea began with Belgian priest and physicist Georges Lemaitre in 1927. He proposed that the universe was expanding from a primeval atom, a super dense hot beginning, and used Einstein's theory of relativity to support it. While other scientists had thought about expanding universes, Lemaitre was first to tie it to a concrete origin point. His idea later evolved into what we now call the Big Bang theory. Number six, the Big Bang happened incredibly fast. Right after the Big Bang, the energy in the universe shot out at the speed of light, about 300 million meters per second. Because of that enormous power and speed, the universe got extremely hot. Estimates say it reached trillions of degrees in just a tiny fraction of a second. Number seven, who coined the term Big Bang? The phrase Big Bang was first used in 1949 by a scientist named Fred Hoyle while speaking on the radio. He didn't mean it as a compliment. He wanted a catchy name to disagree with the idea that the universe had a single beginning. Even though he meant it to criticize, the name stuck, and now Big Bang is how we talk about the start of the universe. Number eight, space itself is expanding. When we say the universe is expanding, we don't mean galaxies are racing through static space. Space itself is stretching. That means if two galaxies are not bound together by gravity, the space between them gets bigger over time. So even though light travels fast, distances grow too. Number nine, did the universe expand faster than light in its first instance? Yes, right after the Big Bang. The universe went through a phase called cosmic inflation. In less than a blink, space itself stretched far faster than the speed of light. This might sound impossible, but it doesn't break Einstein's relativity. Because nothing was flying through space at that speed, instead, space itself was expanding. Thanks to this rapid growth, the universe became smoother and more uniform. Number 10, what is the cosmic microwave background? The CIMB is the faint glow of light left over from the Big Bang, released when the universe first became transparent about 3,800,000 years after its birth. Before that, the universe was so hot and dense that light couldn't travel freely. Today, we detect them as microwave radiation across the whole sky. This baby light acts like a snapshot of the early universe and gives us clues about how everything evolved. Number 11, how was the CIMB discovered? In 1965, two scientists named Arno Penzias and Robert Wilson were using a big radio antenna to study the sky when they noticed a weird, constant hiss in every direction. They tried to remove every possible source of noise, even cleaning pigeon droppings from the dish, but the signal stayed. They later realized that this background noise was actually the leftover glow from the Big Bang, spread throughout the universe. Their accidental discovery gave us powerful proof that the Big Bang really happened. Number 12, the false theory about CIMB. When Penzias and Wilson discovered the cosmic microwave background in 1964, they first thought the mystery noise came from pigeon droppings in their antenna. They cleaned the dish and removed nests, but the static remained. Eventually, they realized they had detected radiation from the early universe. Number 13, Einstein did not accept the Big Bang theory. When Belgian pre-scientist Georges Lemaitre proposed in 1927 that the universe is expanding, coming from a denser, smaller state, Albert Einstein replied, "Vos calculs sont corrects, mais votre physique est abominable." That means your calculations are correct, but your physics is abominable. Einstein was basically admitting Lemaitre's math looked good, but saying he didn't accept the physical idea behind it. Number 14, what rival theory existed to the Big Bang? The main rival was the steady state theory proposed in 1948 by Fred Hoyle, Thomas Gold, and Hermann Bondi. This theory said the universe has no beginning or end. It always existed, expanding, and new matter is continuously created so that its density stays roughly constant. However, the discovery of the cosmic microwave background in 1965 strongly supported the Big Bang theory and challenged the steady state model. Number 15, are there theories of cyclic universes? Yes, some theories suggest that the universe isn't a one-time event but repeats cycles of expansion and contraction forever. One model, called the cyclic or ekpyrotic model, imagines that brains in extra dimensions crash into each other, triggering a Big Bang followed by cooling, expansion, then eventual contraction, and then it all happens again. Number 16, what is the multiverse and bubble hypothesis? The multiverse idea suggests that our universe might be just one among many, like a bubble in a much larger cosmic foam. In the bubble hypothesis, during the rapid expansion phase called eternal inflation, different parts of space stop inflating at different times. Each bubble that stops inflating becomes its own universe, possibly with its own laws of physics or constants. Our bubble is just one in that larger collection. Number 17, the man who predicted the existence of the CMB. In the 40s, George Gamow and his collaborators made powerful predictions about the Big Bang. They realized that if the universe is expanding, then light radiation should be cooling over time. Going back, that meant it was once incredibly hot. They predicted that this leftover light should now appear as cold radiation, what we call the cosmic microwave background. Number 18, what temperature is the CMB today? Today, the cosmic microwave background is extremely cold, about 2.725 Kelvin, which is equivalent to about minus 270.425 Celsius degrees. That cold temperature is because the universe has stretched and cooled over the 13 billion years since those photons began their journey. The precise measurements come from satellites such as COBE, YMIP, and Planck, which map the CMB in great detail. Number 19, is the CMB totally uniform? No, the cosmic microwave background is almost the same in every direction, but there are tiny variations in its temperatures. Differences of only about 1 part in 1000. These little bumps and dips, called anisotropies, come from small density differences in the very early universe. Over billions of years, those small differences grew under gravity into galaxies, stars, and clusters we see now. Number 20, was the universe transparent from the beginning? No, for nearly the first 380000 years, the universe was opaque, filled with a hot plasma of protons, electrons, and photons that scattered light constantly. During this time, photons couldn't travel far without bumping into particles. When the universe cooled enough, electrons and nuclei combined to form neutral atoms in a process called recombination, and light finally could travel freely. Number 21, do we know what caused the Big Bang? We don't know for sure what caused the Big Bang. Current models describe how the universe evolved from an extremely hot, dense state, but they don't explain how or why that state began. Some ideas include random quantum fluctuations, collisions of brains, an object with hidden dimensions, or effects from quantum gravity. But none of these are proven. Number 22, what elements were formed in the first minutes of the Big Bang? In those first few minutes, the universe was hot enough for protons and neutrons to fuse into the lightest elements. Most of what formed was hydrogen and helium, along with smaller amounts of deuterium, a heavy hydrogen, helium-3, and lithium. Heavier elements like carbon, oxygen, etc. came much later inside stars. Number 23, why is the observable universe larger than age for speed of light? Even though the universe is about 13.8 billion years old, the farthest things we see are much farther than 13.8 billion light years away. That's because space itself has stretched and expanded over time, carrying galaxies away from us, So the light we see now traveled through space that was expanding, making the current distance much bigger than what the light would travel in static space. Number 24, how does accelerated expansion affect the size of the universe? Because the universe's expansion is speeding up driven by dark energy, the distances between galaxies are increasing faster over time. That means places we can see keep getting farther apart, and many regions may recede beyond our horizon, making parts of the universe permanently unobservable. Radiant objects once visible could eventually vanish from view. Number 25, you could hear the Big Bang if ears existed. We often say that sound didn't exist at the start of the universe, and that's true in one sense. There were no atoms or air or medium to carry sound waves. However, in the early universe, there were sound-like pressure waves traveling through the hot plasma, a mixture of protons, electrons, and photons. These waves are called baryon acoustic oscillations. But a human ear wouldn't be able to hear them because there was no air or medium as we know it. So the Big Bang was silent in the sense of no conventional sound, but the universe rang with pressure waves very early on. Number 26, how hot was the universe at the beginning? Right after the Big Bang, the universe was unbelievably hot, around 1,000,000 billion degrees, that's 10 to the 15th power Kelvin. At that time, atoms couldn't even exist. Instead, everything was a super energetic soup of tiny particles like quarks and gluons. Number 27, what is cosmic inflation? Cosmic inflation was a super fast growth spurt in the very earliest moments of the universe, happening in a fraction of a second just after the Big Bang. During inflation, space itself stretched out exponentially, growing by a huge factor in almost no time. Number 28, how much did the universe grow during inflation? During cosmic inflation, the universe expanded at an almost unimaginable rate. In a tiny fraction of a second, space itself stretched by a factor of at least 10 to the 26 meters, and likely much more. To see how huge that is, imagine something 1 meter long. After inflation, it would be 10 to the 26 meters, vastly larger than the size of our visible universe today. This ultra-fast expansion is key to explaining why distant parts of the universe appear to have nearly the same temperature and properties, even though they seem too far apart to have communicated. Number 29, what was in the universe right after inflation? Just after cosmic inflation ended, the universe was left very cold and almost empty of conventional particles. The energy stored in the inflation field was released and converted into a dense, hot mix of elementary particles and radiation, a process called reheating. This newly created state was a seething plasma of quarks, gluons, electrons, photons, and other high-energy particles interacting constantly in a hot soup. Number 30, what were quarks in that context? In the early universe, quarks were the most basic building blocks of matter, floating freely in a superhot quark-gluon plasma. Because temperatures were so high, quarks and gluons weren't locked inside protons or neutrons yet. They moved independently. Quarks come in different flavors and carry a special color charge, which lets gluons glue them together. As the universe cooled, quarks began binding into composite particles like protons and neutrons. Number 31, what are gluons and what role did they play? Gluons are the glue particles that carry the strong force, which binds quarks together inside protons and neutrons. In the early universe's quark-gluon plasma, gluons moved among quarks and allowed them to bond as the universe cooled. Because gluons themselves carry color charge, they can interact with each other, making the strong force very powerful and complex. When conditions cooled enough, gluons help quarks lock together, forming stable particles like protons and neutrons. Number 32, when did protons and neutrons appear? Protons and neutrons emerged during the hadronization stage, when quarks cooled enough to bind together via the strong force. This took place during the hadron epoch, roughly between 10 to the minus 6 to 10 to 10 to the minus 4 seconds after the Big Bang. Until then, quarks and gluons formed a hot plasma. After hadronization, protons and neutrons stayed around while many particle and antiparticle pairs annihilated. Number 33. How did protons and neutrons appear? Protons and neutrons formed when the universe cooled enough that free quarks could stick together, a process called hadronization. Quarks grouped in threes, bound by gluons, to make baryons like protons and neutrons. This whole process is explained by quantum chromodynamics, the theory of how quarks and gluons interact via the strong force. Number 34, did atoms exist in the first instance of the universe? No, at first the universe was too hot for atoms. Electrons and nuclei could not stick together, so things existed as a plasma of free particles and photons. Only about 3,800,000 years after the Big Bang, Did the universe cool enough for electrons to combine with nuclei, forming neutral atoms in an event called recombination? Number 35, what about electrons? Electrons are elementary particles. They don't break down into smaller parts. Right after the Big Bang, they existed in a hot, energetic plasma together with protons, neutrons, photons, and other particles. As the universe expanded and cooled, electrons finally had low enough energy to combine with nuclei. Around 380000 years later, many electrons joined with protons to create neutral atoms in a process called recombination, making the universe transparent to light. Number 36, without the Big Bang, would there be chemistry? No, without the Big Bang, there would be no chemistry. The Big Bang created the first atoms and light elements like hydrogen and helium, and then allowed the universe to cool and expand. Over time, these elements combined, formed more complex atoms and molecules, and led to all the chemical reactions we see today. Number 37, why was there no chemistry at the beginning of the universe? At the very beginning, the universe was too hot and energetic. Matter was a plasma of tiny particles like quarks, electrons, photons, moving too fast and too chaotically for atoms to form. Because electrons couldn't stick to nuclei, there were no atoms and so no chemistry. Only when the universe cooled much later, around 380000 years in, could atoms form and chemistry finally began. Number 38, what stopped the nuclear reactions of the Big Bang? The nuclear reactions in the early universe stopped when it expanded and cooled too much. After a few minutes, it became too cold and too thin for protons and neutrons to keep fusing. That's why only very light elements like hydrogen, helium, and a little lithium were made in that first round. Number 39, what happened to antimatter? After the Big Bang, matter and antimatter were created in nearly equal quantities, but for reasons not yet fully understood. Most antimatter disappeared as it was annihilated by matter. This phenomenon is known as matter-antimatter asymmetry and is studied through experiments in particle accelerators and cosmic ray observations. The small difference that survived allowed enough matter to be left over to form galaxies, stars, and planets. Without this asymmetry, the observable universe would not exist today. Number 40. Why did more matter survive than antimatter? Imagine the universe started with almost equal amounts of matter and antimatter. When they met, they would normally cancel each other out, leaving nothing behind. But experiments show that in some rare cases, CI-pi violation causes matter and antimatter to behave slightly differently. Matter is favored just a little bit. Because of that tiny advantage, more matter survived after most of the pairs destroyed each other. This is one of the leading ideas for why we live in a universe made mostly of matter. Number 41, what happened after recombination? Recombination is the time in the early universe when electrons and protons cooled enough to combine into neutral hydrogen atoms. Right after recombination, there were no stars or galaxies yet. The universe was dark and quiet for millions of years. Scientists call this period the cosmic dark ages. Number 42, the epoch of reionization. Around 500 million years after the Big Bang, the first stars and galaxies turned on, and their light started to change neutral hydrogen into charged particles again. That event is called reionization. Number 43, the cosmic dawn, first moments of light. The cosmic dawn is when the first stars lit up, ending the dark ages. This happened about 100 million years after the Big Bang, beginning a new chapter where light filled the cosmos. Number 45, the Big Bang did not instantly create stars or galaxies. When the Big Bang happened, there were no stars or galaxies yet. Everything was super hot and dense. It took millions of years for the universe to cool down, allowing gas, mainly hydrogen and helium, to clump together under gravity, forming the first stars and galaxies. Number 46, what were those first stars like? The very first stars, called population 3, were made almost entirely of hydrogen and helium, the simple elements left over from the Big Bang, with virtually no heavier elements like metals, which affected their evolution and luminosity. They acted like cosmic factories. When these stars exploded as supernovae, they threw those newly formed heavy elements into space, that stellar debris mixed with gas, helping later generations of stars, planets, and even life to have heavier elements. Number 47. When did the first stars form? The first stars appeared around 100 to 200 million years after the Big Bang. Gravity pulled together the primordial gas of hydrogen and helium into dense clumps that became hot enough to start nuclear fusion. These early stars, called population 3, were massive, hot, and didn't contain heavy elements. Their birth also began a new era when the universe became transparent to intense light. Number 48. When did the first galaxies appear? The first galaxies started forming about 400 to 600 million years after the Big Bang, when clouds of hydrogen and helium began to clump together under gravity. These early galaxies were mostly made of those light elements and had few heavy elements or metals. Their birth helped start the process that made the universe more transparent to light, by producing lots of stars and ultraviolet radiation. Number 49, the first galaxies were small and uneven. The earliest galaxies in the universe were small and messy, not the neat spiral or elliptical shapes we see today. They were made mostly of hydrogen and helium with few heavier elements. Number 50, earliest known galaxy 290 million years after the Big Bang. Astronomers using the James Webb Space Telescope discovered a galaxy called Jades GZ 14-0 that formed about 290 million years after the Big Bang. This is extremely early in cosmic history, when the universe was only a tiny percentage of its current age. This galaxy is surprisingly bright and massive for being so young, challenging our ideas about how quickly galaxies could form. Number 51, Big Bang made all the elements. In the beginning, the universe had the right conditions to form the 118 known elements, from hydrogen up to uranium in stars and in cosmic processes afterward. The Big Bang set the stage for these to eventually emerge in stars and supernovae. Number 52, what percentage of the universe is helium due to the Big Bang? Due to the Big Bang, about 25% of the mass of the universe is in the form of helium-4, while the remaining 75% is mostly hydrogen. Other light elements like deuterium, helium-3, and lithium were created too, but in much smaller amounts. Number 53, how was primordial lithium created? Primordial lithium, mostly lithium-7, was formed during Big Bang nucleosynthesis a few minutes after the universe began via nuclear reactions involving light nuclei like helium-3, deuterium, and helium-4. Its abundance is very low, about 1 lithium atom per few billion hydrogen atoms in the early universe. Interestingly, though theory predicts a certain amount, astronomers see less lithium than expected in old stars. That mismatch is known as the cosmological lithium problem. Number 54, era of neutrino decoupling. About 1 second after the Big Bang, tiny particles called neutrinos stopped interacting strongly with other matter. Before that, neutrinos were bouncing around a lot, but as things expanded and cooled, they decoupled, meaning they began traveling more freely through space. Today, those neutrinos still exist as a faint background, though they're incredibly hard to detect. Number 55, carbon detected only 350 million years after the Big Bang. Using the powerful James Webb Space Telescope, astronomers found carbon in a very early galaxy, one that existed just 350 million years after the Big Bang. This is extraordinary because scientists used to think that carbon and other heavier elements would appear much later, maybe around 1 billion years after the Big Bang. Carbon is a key element for life, planets, and organic chemistry. Its early appearance suggests that the universe began creating complex stuff sooner than we expected. Number 56, how metals got enriched so fast? When scientists detect elements like oxygen or carbon so early in cosmic history, it suggests stars must have formed, lived, and exploded very quickly to make those heavy elements. One example, observations detected oxygen in Jades GZ 14-0, even though we'd expect that kind of metal to take longer to accumulate. This forces astronomers to rethink how efficient early star formation and supernovae were. Maybe stars back then burned faster, or supernova ejecta spread elements more widely than we thought. How did heavy elements become abundant so early when the universe had less time to cook them? Number 57, which observation by Edwin Hubble supported the Big Bang? Edwin Hubble supported the Big Bang by discovering in 1929 something amazing. The farther away a galaxy was, the faster it seemed to be moving away from us. This relation is called Hubble's law, and it shows that the universe is expanding. Because of this, scientists realized that if things are moving apart now, they must have been much closer in the past, supporting the idea that the universe started from a small, dense state. Number 58, what did the Hubble Space Telescope do for expansion? The Hubble Space Telescope watched very far, galaxies and supernovae, to measure how fast the universe is expanding. Thanks to its observations, scientists refined the Hubble constant, which tells us how fast galaxies move away as they get farther away. Its data also support that not only is the universe expanding, but the expansion is accelerating over time. Number 59, which space mission studies Big Bang? The space mission studying this theory is the James Webb Space Telescope, launched in December 2021. One of its main goals is to observe the first galaxies and stars formed after the Big Bang, during the period of reionization. Using its infrared and high resolution, the James Webb Space Telescope can see through clouds of gas and dust and capture light from the first cosmic objects, providing data on the universe's earliest moments. Number 60, dust and organic molecules appeared surprisingly early. Using the James Webb Space Telescope, astronomers have found carbon-rich dust grains in galaxies when the universe was less than 1 billion years old. They've also detected complex organic molecules, the kinds of carbon compounds we often associate with life or chemistry, in very early star-forming regions. This means the building blocks of chemistry showed up earlier than people used to expect. Number 61, the Hubble tension. Astronomers use different methods to measure how fast the universe is expanding, and those methods don't agree. That disagreement is called the Hubble tension. One way uses nearby galaxies and stars. Another way uses the oldest light, the CIM by. The trouble is, as our measurements get better, the mismatch is still there. Number 62, a big challenge from the James Webb Telescope. After the James Webb Space Telescope began sending back data, astronomers saw galaxies that looked too big and bright too soon in cosmic history, so soon after the Big Bang that it seemed impossible by our current theories. Some thought that might mean the Big Bang theory was wrong. But later, scientists remeasured those galaxies with better techniques and found they were actually smaller than first thought. So instead of overturning the Big Bang theory, the measurements were refined to fit it again. Number 63, what decides how the universe will end? It all depends on how much dark matter and dark energy there is and how fast the universe keeps stretching. If dark energy stays strong, the universe might expand forever, leading to a big freeze. But if something changes, it could lead to a big rip or even a big crunch, a collapse like Big Bang again. Number 64, what is the big freeze? The big freeze is when the universe keeps stretching out forever. Everything gets farther apart, stars burn out, and things get colder and darker until almost nothing happens. It's like the universe slowly running out of energy. Number 65, what is the big rip? The big rip is a scary idea. It is a scenario in which the expansion of the universe, accelerated by dark energy, increases exponentially until the repulsive forces overwhelm all other interactions, including gravity, disintegrating cosmic structures. In this model, first the galaxies would break apart, then the galaxy clusters, and finally even the atoms would be torn apart. Number 66, what is the Big Crunch? The Big Crunch is a hypothesis about how the universe might end. The opposite of the Big Bang. Instead of expanding forever, the Big Crunch says that one day the universe's expansion will slow, then reverse, and everything will start collapsing inward. Gravity would pull galaxies, stars, and matter back together, making the universe shrink. Eventually, all matter and energy could collapse into an extremely hot, dense point, a singularity, similar to the state from which the Big Bang sprang. Number 67. The Big Bang doesn't tell us how the universe will end. The Big Bang theory describes how the universe began and grew early on, but it doesn't by itself predict how everything ends. That depends on mysterious things like dark energy, dark matter. Scientists must measure those to guess whether the universe will freeze, rip apart, or collapse someday. Number 68. What does it teach us about matter and energy? The Big Bang shows that matter and energy can convert into each other. That energy in the early universe turned into particles like electrons and quarks, and later into atoms. Einstein's famous equation is key here. It links energy and mass. As the universe expanded and cooled, the way matter and energy spread out shaped how stars, galaxies, and everything in space formed. Number 69. Dark matter and dark energy are still mysterious. Although models of the Big Bang and cosmology rely heavily on dark matter and dark energy, we still do not know exactly what they are or how they work. Dark matter is the invisible stuff that seems to hold galaxies together, even though we can't see it. Dark energy is the name we give to whatever is causing the universe's expansion to speed up. Their nature, how they came to exist, and whether they change over time are among the biggest open questions in cosmology. Number 70, the cold spot in the cosmic microwave background. When scientists mapped the leftover light from the Big Bang, the CIMB, they found a spot that is colder than expected, much colder than its surroundings. This cold spot is unusually large, puzzling, and doesn't match the usual small ripples we expect. Some astronomers have suggested there might be a giant supervoid, an underdense region of space in that direction that could make light lose energy as it passes through, causing it to appear colder. Number 71, the first echoes still reach us. The cosmic microwave background is light that left the universe about 3,800,000 years after the Big Bang. Because light travels at a finite speed, what we see in the CIMB is like a baby picture of the universe. It's the earliest light we can observe. That means we are literally seeing echoes from the universe's infancy and Big Bang. It also carries tiny temperature differences that tell us about early structure formation. Number 72, cosmic inflation was the fastest expansion ever known. Just after the Big Bang, the universe is thought to have gone through a phase called inflation, during which space itself expanded incredibly fast, much faster than the speed of light. This rapid expansion helps explain why the universe looks so uniform and why distant parts look similar. Number 73. We don't know the initial conditions of inflation. The idea of inflation, a super fast stretch of space right after the Big Bang, helps explain many things, like why distant parts of the universe look similar. But the start of inflation is mysterious. We don't yet understand what triggered it, what energy field drove it, or exactly how inflation ended. These initial conditions are one of the big puzzles in cosmology, where theory is ahead of observational proof. Number 74, what did the Planck satellite do? The Planck satellite made the clearest picture ever of the cosmic microwave background, the faint glow left over from the Big Bang. With that map, scientists could tell how old the universe is, how much matter and dark energy it has, and what shape it is. Number 75, the Euclid Space Telescope, the Euclid Telescope, launched in 2023, is making a giant 3D map of galaxies. It measures how many galaxies there are, where they are, and how they move. By doing that, it helps scientists see how the expansion of the universe from the Big Bang acts over time. It also helps us understand dark energy, the mysterious force pushing the universe to get bigger faster. Number 76, the Vera Rubin Observatory. The Vera Rubin Observatory, coming online in 2025, will survey the entire night sky repeatedly. It will capture images of billions of galaxies over time. With that, astronomers hope to trace how the universe expanded after the Big Bang and learn more about dark energy. Number 77, can we recreate Big Bang conditions in labs? Yes, in particle accelerators like the Large Hadron Collider. Scientists smash particles together at extremely high energies. These collisions mimic some of the extreme hot and dense states that existed just after the Big Bang. They let us study quarks, gluons, and how matter behaved under extreme conditions, though we can't recreate the whole universe. Number 78, the image of an explosion is misleading. Many people imagine the Big Bang as a big fireball exploding in space, with a loud boom and shockwaves, but that's wrong. The Big Bang was more like space itself stretching and getting bigger everywhere at once. So there was no boom or explosion noise, just a really fast expansion of the very fabric of space. Number 79, what are cosmic voids? Cosmic voids are enormous empty spaces in the universe where there are very few galaxies. Most of the universe's matter is gathered in filaments and clusters, so the spaces in between those structures become voids. They reflect how small density differences in the early universe grew over time. Voids can be huge, tens to hundreds of millions of light years across, and even though they seem empty, they can contain a little matter. Like faint galaxies. Number 80, why is it an accepted theory today? We believe in the Big Bang theory because many observations match its predictions. For example, we see that faraway galaxies are moving away from us, meaning the universe is also, we detect the cosmic microwave background, the faint leftover glow from the early universe, plus the amounts of hydrogen, helium, and lithium in space match what the theory predicts. Number 81, the cosmic neutrino background was formed 1 second after the Big Bang. About 1 second after the Big Bang, neutrinos broke free and started flying through space. They're ultra faint and almost never interact. So no detector has seen them directly yet. We know they're there from tiny effects they leave in cosmic patterns. Number 82, the CIMB is the most perfect black body ever measured. Imagine drawing the smoothest curve ever, with no bumps. Now zoom in 1,000,000 times and look for tiny bumps. COBE found that any bump is smaller than 50 out of 1,000,000. That's like 5 cents on $1,000,000. So the CIMB light follows the perfect black body curve almost exactly. This tells us the early universe mixed its light and matter really, really well. Number 83, what philosophical questions does the Big Bang raise? The Big Bang makes us wonder deep things like, why is there something rather than nothing? Did time itself have a beginning? Are we just part of a much bigger story we can't fully see? It also makes us think about the limits of what we can ever know, whether some answers are beyond science. Number 84, what does it reveal about our place in the universe? The Big Bang shows that Earth, stars, and people are all made from the same cosmic processes. We are part of the universe's story, not separate from it. It tells us we don't occupy a special or central place. Our home is just one region in a vast cosmos. It also reminds us that the atoms in our bodies were once inside stars, so we are literally made of stardust. Number 85, the Big Bang doesn't describe the before. The Big Bang theory gives a model for how the universe evolved from its earliest moments onward, but it says almost nothing about what came before, or whether that question even makes sense. Some scientists propose ideas like quantum gravity, bouncing universes, or other models, but none are confirmed yet. Number 86, is the universe still cooling since the Big Bang? Yes, the universe is still cooling since the Big Bang because of its continued expansion. As space stretches, the energy of the radiation is scattered, reducing the average temperature of the cosmos. Currently, the temperature of the cosmic microwave background is about 2725 Kelvin, much lower than in the first instance. This constant cooling is consistent with astronomical observations and models of the expanding universe. Number 87, how important was the Higgs boson in the Big Bang? The Higgs boson, or more precisely the Higgs field, is very important because it gives mass to many fundamental particles like quarks and electrons. Without it, those particles would be massless and couldn't form protons, neutrons, or atoms. The Higgs idea was validated in 2012 when experiments at the Large Hadron Collider discovered the Higgs boson. Number 88, universe's age versus old stars paradox. For a while, some scientists found stars whose estimated ages were older than the estimated age of the universe. That doesn't make sense. A star can't be older than the entire universe. This paradox helped push astronomers to improve their measurements of distances, brightnesses, and models to resolve the inconsistency. Number 89, the idea of a dark Big Bang. Some scientists propose a speculative scenario. Maybe dark matter had its own special Big Bang or creation event, a dark Big Bang either separate from or happening just after the ordinary Big Bang. In that case, dark matter, which we can't see directly, would have formed through a different process. Number 90, the flatness problem demands huge precision. Our observations show the universe is extremely flat in a geometry sense, not curved much at all. For that to be true, the density of matter and energy in the early universe had to be almost exactly the critical density. If the density had been even a little different, the universe today would look very curved or would have collapsed. Number 91, the universe should have collapsed. The Bentley paradox. One old idea, known as the Bentley paradox, says if all stars attract each other by gravity, then over time they should pull each other and collapse into one big clump. But that didn't happen. This paradox is one reason why people in older times doubted a static universe. It suggested a static universe couldn't last stably forever, unless something else stops collapse. Number 92, quantum fluctuations might have seeded everything. In the very earliest universe, even empty space had tiny random fluctuations in energy because of quantum mechanics. Those tiny wiggles got stretched out during inflation and became the seeds for all the structure. Galaxies, stars, clusters we see today, without those quantum fluctuations, the universe might have been perfectly smooth with nothing interesting forming. Number 93, Big Bang, nucleosynthesis tests all four fundamental forces. In the first few minutes after the Big Bang, the universe created light elements like hydrogen, helium, lithium. This process, called nucleosynthesis, depends on all four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Because of that, studying the amounts of light elements we see gives clues about how all these forces behaved in the early universe. Number 94, was gravity the first fundamental force to act? Many cosmologists believe that just after the Big Bang, the four fundamental forces, gravity, electromagnetism, weak nuclear, strong nuclear, were once unified. As the universe cooled, they separated. Gravity is thought to have separated first, becoming distinct while the universe was still extremely hot and dense. We don't have direct proof of this, but it fits with theories about how forces unify and break apart as the universe expands. Number 95, gravitational waves from the first instance. In the first tiny fractions of a second after the Big Bang, space and time were so violent and energetic that ripples called primordial gravitational waves could have been produced. These ripples stretch and squeeze space-time itself, carrying information from that early era. Scientists hope to detect them someday, but they are extremely faint and buried under many stronger signals from more recent cosmic events. If we ever measure them, those waves could tell us about the very beginning of inflation and conditions that no telescope can reach. Number 96, the expansion rate of the universe is measured by the Hubble constant. Astronomers use something called the Hubble constant to tell how fast the universe is expanding. The farther away a galaxy is from us, the faster it seems to be moving away. That's what Hubble's law says. So if Galaxy A is twice as far away as Galaxy B, Galaxy A appears to recede twice as fast. Scientists measure the redshift to figure out how fast galaxies move away. That redshift gives clues to the expansion speed. The Hubble constant is one of the key numbers in cosmology because from it we can estimate the age of the universe and how it has changed over time. Number 97, a gamma-ray burst that rivaled the universe's energy. In 1997, astronomers detected a gamma-ray burst called GRB 971214. At first, they estimated it released as much energy in a few seconds as all the rest of the universe put together. Later, scientists realized that the energy was likely less extreme because the burst was probably focused toward us rather than in all directions, but it was still one of the most powerful cosmic explosions ever recorded, pushing models of how these bursts can form. Number 98, is the observable universe the entire universe? No, the observable universe is just the part we can see or could see because light from those regions has had time to reach us. Beyond that is more universe we can't observe. The total universe might be far larger, maybe infinite, based on cosmological models. Number 99, the Big Bang theme song origin. The theme song for the Big Bang Theory was written and performed by the band Bare Naked Ladies. The writers asked Ed Robertson to write a short history of everything in under a minute, and he used ideas about the universe's origin to make the lyrics. Even though the band hesitated at first, they agreed once they saw the show's style and liked the idea. Number 100, George Smoot won $1 million. George Smoot is a famous physicist who studied the leftover light from the Big Bang the sea I am by. He also appeared on the TV quiz show Are You Smarter Than a Fifth Grader? And won $1 million. That's a fun twist. A scientist known for cosmology also winning a game show prize. He's one of the only people to do that. And that's all. What Big Bang fact surprised you the most? Leave it in the comments and subscribe. See you soon, your friend Neil.